All right, now that we have seen how permutations and combinations can be used to find how many ways things can happen, we can actually use these in probabilities. So again, the probability in general, the probability of event A is just going to be the number of ways event A can happen over the total number of outcomes. So if we could just use this kind of principle, we can use combinations and occasionally permutations to find some somewhat more difficult probabilities that would be hard with normal rules, but with permutations, combinations are quite simple. So let's look at this first example. It says on a lottery, an urn containing balls numbered 1 to 54 is used to draw 6 numbers out without replacing the balls. You can bet $1 and get 2 sets of 6 numbers. To win, all 6 numbers must be selected. What is the probability of winning this lottery? So we have 54 balls. You can think of it as balls 0, 1 to 54, something like that. And our goal is to say, what's the probability we win this lottery? Now, the key thing here is don't think about pulling one ball out of a time. Think about you have all these balls in this hopper. And when we pull them out, we just pull out a set of 6 numbers. Okay? So obviously there's no duplicates or anything like that. So we're not going to have 2 of the same ones. We're just going to have these 6 numbers. So if I think of the different combinations I can have, essentially I have 54 balls and I'm picking 6 of them. So I have 54 balls and I'm choosing 6 at a time. And if you're thinking, does the order matter? Well, it really doesn't. Because if you get the lottery, if you have your balls out of order, you can just switch the balls because they're all unique. So the total number of lottery combinations in this drawing is 54, choose 6. 54 balls, and you're choosing 6 of them at a time. So this is the number of ways, number of lottery numbers you can have for this. And if you work this out with a calculator or something, this is a pretty big number. This is 25,827,165. So the question is, how many ways do I win this lottery? Well, when I spend my $1, I get 2 sets of numbers, only 2. So of all these 25 million combinations, there's only 2 that I win with. And those would be the 2 that are on my ticket. So the probability of winning this lottery is 2 out of 25,827,165. Or not very good, obviously. Now, in general, with these problems, if you would leave your answer just like this, 2 over 54, choose 6, I'm pretty happy with that. You don't have to figure out the actual numbers. If you want to and actually see what the probability is, that's great. And I'll do it for a couple of them, but we don't have to do that for all of them. So let's look at this example. It says a shipment of 120 fasteners contains 4 of them that are defective, and they're sent to a plant. The quality control manager selects 5 fasteners and inspects them. What is the probability exactly 1 out of the 5 is defective? Okay. So we want to know what's the chance 1 out of 5 are defective. Another way to say this probability, we basically want 1 defective and 4 not defective. Okay. It means the same thing. Now, this is important that we're saying exactly 1 out of the 5. Now, we don't care which one. It can be the first, the second, the third, the fourth, whatever. But we just want 1 out of the 5. So, just a obviously quick note. If there's 120 fasteners sent to this plant, there are 4 defective of them. So that means there's 116 that are not defective, obviously. So, when I'm finding this probability, first I'll find the total number of ways that can happen. So there's 120 fasteners, and I'm picking 5 of them at the time. So my total number of ways this can happen is 120, choose 5. And it's a combination, because again, I don't care which fastener is defective. I don't care if it's the first, second, third, fourth, fifth. I just want 1 out of the 5 to be defective. So I'm picking those 5 out of the 120. Now, you can think about this in 2 ways. I'm going to kind of think about it in this philosophy that I want 1 of the defectives and 4 of the not defectives. And I'm going to set those up with individual combinations. So since I want one of these 4, I want one of these and I want 4 of these. I want both these things to happen. And remember we say we want 2 things at the same time, this and we're going to multiply. So I want 1 out of those 4 defective fasteners, and, so since it's and, I'm multiplying, I want 4 out of the 116 not defective. So this is how we find our probability. 1 out of the 4 that are defective, 4 out of the 116 that are not, total of 120, choose 5. Now again, this is something you could literally put these in your calculator. I did this one. This turns out to be 0.1503. And you can try it in your calculator. Obviously, make sure you put the parentheses and everything in there when you're doing your combinations, but you should get the same number. All right, let's look at this problem where we have a box with some marbles in it, or not marbles, jelly beans, something with different colors. So this box has 18 yellow, 24 green, and 33 red jelly beans. So if we add that up, that is a total of 75 total beans. And we're going to pick 13 of them at a time. Okay? So we're picking 13 at a time. And so our first probability says, what's the probability all 11 are yellow? Or 11 are yellow, not all 13, obviously. So we want 11 yellow. And so since we're picking 13, we can say 2 are not yellow. So this is essentially what we're looking for. So this is very similar to the fastener problem that we just did. The only difference is not yellow can be 2 things. Not yellow can be green or red. So how I'll do it is, first of all, when I do the actual total number, well, there's 75 beans, and I'm picking 13 at a time. Again, I don't care the order of the beans. The 11 can be the first 11, last 11, middle 11, doesn't matter. So I'm using a combination. And in most probability problems, combinations is the way we will use it. Now, there are 18 yellow jelly beans, and we want exactly 11 of those. So for that part, I'm going to say I want 18, choose 11. So I want that to happen. And, so I'm going to multiply, I want 2 of the not yellow. Well, for the not yellow, it could be the 24 green or the 33 red. So we're saying or, so we'll kind of put those together. So that's a total of 57 not yellow. So I want 11 of the 18 yellow, and I want 2 of the non-yellow. So this would be our probability. So 18 choose 11 times 57 choose 2 over 75 choose 13. And I did go ahead and not work this probability out. It's 0.0000401. So obviously not a very good chance that that happens. Now conversely, let's look at B. Now B says I want 11 yellow and 1 green. Well, we're still picking 13 beans, and there's still 1 unaccounted for. So if it's not yellow and it's not green, it would have to obviously be red. So there's 1 red. So now we're kind of specifying what they're all going to be. So the only difference in this one, we still do 75, choose 13. But now on the top, we are going to do 18, choose 11. But now we don't want 2 to be from some generic not yellow pool. We want them actually to be green and red. So we want 1 of the green. So 24, choose 1. And then we want 1 from the red, which is 33, choose 1. And again, you can notice they all add up to 13, 11, 1, and 1. 18, 24, and 33 all add up to 75. Now this probability is going to be smaller because you're more specific what happens with those last 2. And I did figure this out. That's 0.000000199. It's about half as likely when you actually specify what those last 2 have to go to. Now finally, we have this last one, which could be a really hard problem if you don't know the trick. It says at least 1 is yellow. Well, at least 1 is yellow could be a lot of things. That could be the probability you get 1 yellow and 12 not. Or it could be the probability of 2 yellow and 11 not. And you could keep doing this over and over and over again because at least one yellow is one or more. So whenever you have these at least problems, we kind of use the trick that instead of doing that, let's just go ahead and say, I'll do 1 minus the probability of no yellow will give us the probability of at least one yellow. So 1 minus the probability of no yellow, because the only way you don't get at least one yellow is if there's no yellows, if they're all some other color. So if I just take away that outcomes, then everything else is going to have at least one yellow. So if I do the probability of no yellow, well, I want them all to be from the not yellow patch. So it's 75, choose 13 on the bottom. And if you recall, there were 57 not yellow. And so I just want all 13 from that batch. Now, if you want to be more specific, then you could also say 18 choose 0 because I want none of the yellow. But 18 choose 0, anything choose 0 is 1. So you're multiplying it by 1, so it doesn't change anything. But if that kind of keeps you accounting for the 75 total and the 13 plus 0, that is fine too. All right, let's look at one more example with a probability combinations, and this is talking about poker. So in poker, we'll draw 5 cards at once, and then we want some different outcomes. So we'll draw 5 cards out of the 52, and then we'll want some differing things to do. For this first example, we'll just do what's called a full house. Now in a full house, you want 3 of these cards to match, and then you want these last 2 cards to match as well. Now, obviously, they can't match each other because then that would be 5 of the same card, and we know that there's only 4 of each card. So, for example, I could have 3 aces and 2 twos. I could have 3 twos and 2 kings. There are lots and lots of combinations. So when I'm doing a probability of a full house, the one trick about this is essentially we're going to find the probability of getting 3 of a kind and the probability of getting 2 of a kind at the same time. So first we know there's 52 cards, and I'm picking 5 at a time. I'm just drawing these 5 out of the deck, so that's going to be my total number. Now on the top, I want to get 3 of a kind. So let's talk about the aces, for example. Well, if you think about how many aces are in the deck, there are 4 aces, and I'm trying to get 3 of them at the same time. Now here's the problem. That is fine for aces, but what if it's a 2? What if it's a 3? What if it's a 4? It can technically be 13 different cards. It could be 3 aces, 3 twos, 3 threes, 3 fours, etc., etc. So there are actually 13 times 4 choose 3 ways to get 3 of a kind. Now a similar thought will happen for the pair, because this is my 3 of a kind. All the different 3 of a kinds can happen. So for my pair, for the 2 that match, I'm going to pick 2 out of the 4 cards. And now it's not 13 different things that can happen because one of the cards is already my 3 of a kind. So if that's my 3 of a kind, that can't be my pair now. You can't be the pair and the 3 of a kind. So now there are only 12 possibilities for my pair. So we have 13 times 4 choose 3 times 12 times 4 choose 2. Over 52 choose 5. So if you work this out, this becomes 0.00144. So it's about 0.144% of the time you'll get a full house. So not very likely at all. All right, we'll look at some more of these combination probabilities when we return from break. We'll look at some other kind of probabilities. So hopefully this is kind of a quick introduction, get you thinking about how we can do these probabilities with combinations.